welcome to this problem walkthrough. Today, we'll be exploring a problem titled Counting Words with a Given Prefix. In this session, we'll discuss the problem statement, think through the solution intuitively, and break it down step by step to help you understand the approach. Let's dive in. In this problem, we are tasked with determining how many strings in an array start with a given prefix. The input consists of two components, an array of strings called words, and a string called pref, which represents the prefix we are looking for. A string from the array is considered a match if it begins with the prefix pref. The goal is to return an integer, which represents the total count of strings in the words array that satisfy this condition. The strings in the words array, as well as the prefix pref, will only contain lowercase English letters. This ensures that we are working with simple alphabetical inputs, and the output will always be a single integer that represents the count of matches. Let's look at the first example to understand the problem more clearly. Here, the input array is words equals, pay, attention, practice, attend, and the given prefix is pref equals at. Our task is to count how many of these words start with the prefix at. If we examine the words, we see that attention and attend both start with at, while pay and practice do not. Therefore, the total count of matching words is 2, which is the output for this example. Now, consider the second example. The input array is words equals, LeetCode, win, loops, success, and the prefix is pref equals code. Here, we need to check if any of the words in the array start with the prefix code. Examining each word, we find that none of them begin with this prefix. As a result, the output for this example is 0, because there are no matches. Lastly, let's review the third example. The input array is words equals, apple, app, apricot, anchor, and the prefix is pref equals ap. Among these words, apple, app, and apricot all start with the prefix ap, while anchor does not. This gives us a total of 3 matching words. Therefore, the output for this example is 3. Additionally, it's important to consider constraints in edge cases, such as when the prefix is empty, when there are no matches, or when the prefix is longer than a word in the array. These scenarios will help ensure that we handle all possible inputs effectively in our solution. To begin, let's consider the brute force approach, which is the most straightforward way to solve this problem. The intuition behind this method is to iterate through each word in the array and check if it starts with the given prefix. In Python, we can use the starts with method or slice the string to compare the relevant portion with the prefix. The steps are simple: initialize a counter to 0, loop through each word, and use word.starts-with pref to check if it matches the prefix. If it does, increment the counter. Finally, return the counter after going through all the words. In terms of complexity, this approach has a time complexity of O, n asterisk k, where n is the number of words and k is the length of the prefix, as the starts with operation could take O, k, in the worst case. The space complexity is O, 1, since we only use a counter. While this approach is simple and easy to implement, its performance can degrade for large inputs because of repeated string operations, which is a trade-off to consider. Now, we move on to an optimized approach that improves on the brute force method by introducing an early exit condition. The key intuition here is that if a word is shorter than the prefix, it cannot possibly match, so we can skip the starts with check altogether for such words. The steps are as follows: initialize a counter to 0, then iterate through the words. For each word, first check if its length is greater than or equal to the prefix length. If not, skip the word entirely. Otherwise, proceed with the starts with pref check. If the word matches the prefix, increment the counter. Finally, return the counter. While the worst-case time complexity remains O, n asterisk k, similar to the brute force approach, the early exit condition reduces the number of operations for datasets with many short words, leading to improved practical performance. The space complexity is still O, 1, which is an advantage. This approach balances simplicity and efficiency, making it a slight improvement over the brute force method. Another alternative we could consider is using Python's built-in filter function. This approach leverages the functional programming paradigm to simplify the process. Instead of manually iterating through the words, we use filter, along with a lambda function to keep only the words that start with the prefix. We can then calculate the length of the resulting filtered list or use sum to count the matches. The time complexity remains O, and *k, since the filter function still has to check each word, and the space complexity increases to O(n), because the filtered list is stored in memory. The trade-offs here include a more concise and Pythonic implementation, but the additional memory usage makes it less suitable for scenarios with large input sizes. While this approach is elegant and easy to write, the extra space requirement could be a limiting factor for memory-constrained environments. Among the approaches discussed, we chose the optimized brute force method as the best strategy. This decision was based on several factors. First, the simplicity of the implementation makes it easy to understand and maintain. Second, while the time complexity is the same as the brute force approach, the early exit condition offers practical performance improvements by avoiding unnecessary checks. Third, it is space efficient, as it does not require additional memory like the filtering approach. The key insight here is that the problem boils down to checking the starts with property for each word, a process already optimized in Python's string library. Adding a length check further enhances efficiency by skipping irrelevant words. Compared to the alternatives, this method avoids the performance drawbacks of brute force and the memory overhead of filtering, making it a balanced and effective solution for the problem. The chosen approach strikes an effective balance between simplicity, clarity, and efficiency. While it may not be the absolute fastest in every edge case, it offers a practical and reliable solution for the given problem constraints. The early exit condition ensures that unnecessary operations are minimized, and the lack of additional memory requirements keeps the approach lightweight. These trade-offs make it an excellent choice for solving this problem in most scenarios. Overall, it is a robust and well-rounded strategy that addresses the key aspects of performance and implementation simplicity without introducing significant drawbacks. To solve the problem of counting words with a given prefix, we can start with a straightforward brute force approach. First, we initialize a variable called count and set it to 0. This variable will help us track the total number of words that match the given prefix. Next, we iterate through each word in the words array using a for loop. For every word, we check if it starts with the specified prefix pref. Python provides a convenient built-in method called startsWith, for this purpose, which directly checks if the word begins with the given prefix. Alternatively, we can slice the word to match the length of the prefix and compare it manually to pref. If the condition is true, we increment the count variable by 1. This step-by-step process ensures that we examine every word in the array for a potential match. Once we've iterated through all the words in the array, we simply return the final value of the count variable. This gives us the total number of words that start with the given prefix. Using the startsWith method is particularly advantageous because it is optimized for prefix checks in Python, making the code more concise and reliable. It also handles edge cases, such as when the prefix is longer than the word, without requiring additional checks. Speaking of edge cases, there are a few important ones to consider. If the words array is empty, the result is 0 since there are no words to check. If the prefix itself is empty, every word in the array is considered to start with it, so the result is simply the length of the words array. Additionally, if the prefix is longer than any word in the array, the result is 0, as no word can have such a prefix. Lastly, the algorithm assumes a case-sensitive match, meaning that uppercase and lowercase letters are treated as distinct. In terms of complexity, the algorithm is efficient for small to medium-sized inputs. The time complexity is O, and *p, where n is the number of words and p is the length of the prefix, while the space complexity is O(1), since we only use a counter variable. Breaking the problem down further, the data structures involved are straightforward. The input consists of a list of strings called words and a string pref that represents the prefix we are matching. The output is a single integer, which is the count of words that start with pref. For intermediate storage, we only use a single counter variable, count, to keep track of the running total. This simplicity ensures that the algorithm is space efficient. While the brute force approach is sufficient for small to medium-sized inputs, we can consider optimizations for larger datasets or frequent prefix checks. For instance, if the input list is sorted or if prefix lookups are performed repeatedly, using a tree data structure could significantly speed up the process. However, for this problem's scope, the brute force approach is both efficient and effective. Here's the implementation of the algorithm in Python. We define a function count underscore words underscore with underscore prefix that takes words and pref as arguments. Inside the function, we initialize the count variable to 0. Then, we use a for loop to iterate through each word in words. For every word, we check if it starts with the prefix using the starts with method. If it does, we increment the count by 1. Finally, we return the value of count after the loop completes. To illustrate how the algorithm works, let's consider an example. Suppose we have the input words equals apple, apply, banana, app, and pref equals app. When we call the function count underscore words underscore with underscore prefix with these inputs, it initializes the counter to 0. During the first iteration, it checks if apple starts with app. It does, so the counter is increment to 1. In the second iteration, it checks apply. This also starts with app, so the counter becomes 2. In the third iteration, it checks banana. This does not start with app, so the counter remains 2. Finally, in the fourth iteration, it checks app. This starts with app, so the counter is increment to 3. The function then returns 3 as the result, which is the correct count of words starting with the prefix. We can also examine a few edge cases. If the words array is empty, the function simply returns 0 as there are no words to check. If the prefix is empty, every word matches, so the result is the length of the words array. If the prefix is longer than any word, the result is 0. These examples demonstrate the algorithm's robustness in handling a variety of scenarios. Finally, let's touch on another edge case, case sensitivity. For example, if the words array is apple and the prefix is a, the result is 0 because the algorithm assumes a case-sensitive match, and apple does not start with lowercase a. By breaking the problem into steps and addressing edge cases, we ensure that the algorithm is both clear and correct. This simple yet effective approach allows us to confidently solve the problem of counting words with a given prefix across a wide range of inputs. This Python implementation solves the problem of counting words with a given prefix using a simple and efficient approach. The function prefix count is defined within a class solution, following the convention used in LeetCode problems. The function takes two inputs, words, a list of strings, and pref, the prefix to look for. It starts by initializing a variable count to 0. This variable will be used to keep track of how many words in the list start with the given prefix. Next, the function iterates over each word in the words list using a for loop. For each word, the method starts with is used to check if the word begins with the prefix pref. The starts with method is efficient and checks this condition in o, len, pref, time for each word. If the condition is true, the count variable is increment by 1. After iterating through all the words, the function returns the value of count, which represents the total number of words that start with the given prefix. This solution is efficient with a time complexity of o, n asterisk len, pref, where n is the number of words in the list. The space complexity is o, 1, as no additional space is used beyond a few variables. This approach handles all edge cases, such as when words is empty or when no words match the prefix, by correctly returning 0 in such cases. Overall, this implementation is clean, concise, and well suited to the problem requirements. This is the Java implementation of the LeetCode problem number 2185, counting words with a given prefix. The code mirrors the logic from the Python version but incorporates Java-specific syntax and features. The method prefix count accepts an array of strings, words, and a string prefix, pref. It iterates through the array, checking if each word starts with the given prefix using the starts with method, and counts the matches. Key differences from Python include explicit type declarations for variables and method signatures, as well as the use of Java's enhanced for loop for iteration. To solve the problem of counting words with a given prefix, let's start by walking through our first example. Here, we have a list of words, apple, apricot, banana, and apex. The prefix we are looking for is ap. The first step is to initialize a variable called count and set it to 0. This variable will help us keep track of how many words start with the given prefix. Now, we iterate over the list of words one by one. For the first word, apple, we check if it starts with the prefix ap using the starts with method. Since it does, we increment our count by 1, making it equal to 1. Moving to the second word, apricot, we again check if it starts with ap. The
The condition is true, so we increase count by another 1, bringing it to 2.
Next, we evaluate the third word, banana. Using the starts with method, we find that it does not start with AP, so the count remains unchanged at 2. Finally, we check the last word, apex. It does start with the prefix AP, so we increment count by 1, making it 3. At this point, we have finished iterating through all the words in the list. To conclude this example, we return the value of count, which is 3. This means there are 3 words in the list that start with the prefix AP. Now, let's look at a second example where no words match the given prefix. Here, our input words are dog, cat, fish, and elephant, and the prefix is by. We begin just as before by initializing our variable count to 0. Then, we start iterating through the list of words. For the first word, dog, we check if it starts with the prefix by. Since it doesn't, the condition evaluates to false, and count remains 0. We continue to the next word, cat, and perform the same check. Again, the condition is false, so count stays at 0. For the third word, fish, we find that it also does not start with by, leaving count unchanged at 0. Finally, we evaluate the fourth word, elephant, to see if it starts with the prefix by. Once again, the condition evaluates to false for elephant, so count remains at 0. Having checked all the words in the list, we can now return the value of count, which is 0. This result indicates that none of the words in the list start with the prefix by. Now, let's move on to a third example where all the words in the list match the given prefix. The input words are star, start, stark, and starfish, and the prefix is star. As usual, we start by initializing count to 0. We then iterate over each word in the list. First, we check the word star. It starts with star, so we increment count by 1, making it 1. Next, we evaluate the word start. It also starts with star, so we add another 1 to count, bringing it to 2. Moving on, we check stark. Since it starts with the prefix star, we increase count by 1 again, making it 3. Finally, we check the last word, starfish, which also starts with star. This results in another increment of count by 1, making the total 4. At the end of this process, we return the value of count, which is 4. This indicates that all 4 words in the list start with the prefix star. By walking through these examples, we can see how the solution consistently and efficiently counts the number of words matching the given prefix, regardless of the input. To understand the time complexity of the solution, we start by analyzing the 2 main operations performed. First, the algorithm iterates over the words list using a for loop. If the words list contains n elements, this loop will execute n times. Next, for each word, the starts with method checks whether the word begins with the given prefix pref. If the prefix has a length of m, the starts with method compares up to m characters of the word. In the worst-case scenario, where all words need to be checked and the prefix length is significant, this comparison takes m time for each word. Combining these 2 operations, the total time complexity becomes n*m, where n is the number of words and m is the length of the prefix. In the best case, when the prefix is empty, the starts with method only takes 1 time per word, resulting in an overall complexity of n. Therefore, the worst-case time complexity is n*m. The space complexity of the solution is determined by input storage, auxiliary variables, and any intermediate operations. For input storage, the words list and the prefix pref are provided as inputs. The space required for these inputs is n for the words list and m for the prefix, where n is the number of words and m is the length of the prefix. Additionally, the algorithm uses a single integer variable, count, which tracks the number of words matching the prefix. This variable requires only 1 space. The starts with method does not require any additional space, as it operates directly on the given strings. Combining these factors, the total space complexity is the sum of the input storage, n plus m, and the auxiliary space, 1. As a result, the overall space complexity is n plus m. When comparing this approach to a brute force solution, we notice that both would result in a time complexity of n*m. Using a brute force method, we would manually iterate over each character of each word and compare it to the prefix character by character. However, the starts with method is optimized and implemented in C, making it significantly faster in practice. The current solution is already optimized for the problem's constraints, and further optimization is challenging since checking prefixes inherently involves examining the start of each word. Now, let's analyze the time complexity in different cases. In the best case, where the prefix is empty, the starts with method takes O(1) per word, leading to a total complexity of O(n). In the average case, with a moderate prefix length, the time complexity becomes O(n*)m. In the worst case, for long words and a long prefix, the complexity is also O(n*)m. To formally prove the big O complexity, consider that the outer loop iterates over n words, and within each iteration, the starts with method performs a prefix check with a complexity of O(m). This results in a total time complexity of O(n*)m equals O(n*)m. For space complexity, we account for the input storage, which requires O(n) for the words list and O(m) for the prefix. Additionally, the algorithm uses only a constant amount of auxiliary space, O(1), for the count variable. Combining these, the total space complexity is O(n plus m). Thus, the solution is efficient in both time and space for the given problem constraints. Here are some common mistakes to watch out for when solving this problem. First, forgetting to handle edge cases, such as when the prefix is longer than the words being checked. This can lead to silent failures or incorrect results, as functions like starts with or string slicing won't behave as expected in these situations. Always validate the input lengths to prevent this. Another issue is performing inefficient checks for all words. For example, using a naive loop and not terminating early when possible can make your solution slower than necessary. Instead, optimize by focusing only on the comparisons that are truly needed. Additionally, be cautious about modifying the input array. If the same array is reused elsewhere in your code, altering it, like sorting, can introduce unintended side effects. To avoid this, always work with a copy of the array if modifications are required. Lastly, a common misunderstanding is comparing the entire string to the prefix, rather than just the starting substring. This can lead to incorrect logic, so be clear on what the problem is asking for. Another important point is to consider case sensitivity in your comparisons. Overlooking whether comparisons should be case sensitive or not can result in mismatches. If the problem specifies that the comparison is case insensitive, you can normalize the inputs by converting them to lowercase using methods like word.lower. Now, when it comes to interviews, this problem is often used to test your understanding of string manipulation and efficient traversal techniques. Recognizing when to use built-in methods like starts with versus manual slicing is a valuable skill. Interviewers may also explore your ability to optimize early, such as discussing the trade-offs between a brute force approach and more efficient techniques like using a tree or binary search. Additionally, scalability is a key topic. Be prepared to analyze the time complexity of your solution, for example, n*k, for a brute force approach where n is the number of words and k is the average word length. Finally, interviewers might introduce follow-up variations, such as asking you to return all words with the prefix instead of just counting them, or even handling dynamic updates to the prefix. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 14, longest common prefix, focuses on finding the common prefix among an array of strings. Another related problem is LeetCode 208, implement tree, which introduces efficient prefix matching using a tree data structure. LeetCode 648, replace words, involves replacing words in a sentence based on a dictionary of prefixes, while LeetCode 820, short encoding of words, tackles efficient string encoding with a focus on both suffixes and prefixes. When approaching this problem, you can also consider alternative strategies. A brute force approach involves checking each word in the array to see if it starts with the given prefix. While this method is simple to implement, its time complexity is n*k, which can be inefficient for large datasets. This trade-off between simplicity and efficiency is a key consideration when evaluating different approaches. For more advanced solutions, consider using a tree or prefix tree. By building a tree from the words array, you can achieve efficient prefix searches with a time complexity of k for both insertion and lookup, where k is the length of the prefix. The trade-off here is the additional memory overhead required to maintain the tree structure, but this approach can be significantly faster for repeated prefix queries.
Another option is binary search.
By sorting the words array first, you can use binary search to quickly find the range of words that start with the prefix. This approach has a time complexity of O, n log n, for sorting and O, k log n, for the search itself. While sorting adds pre-processing overhead, it makes prefix queries much more efficient. Lastly, you can use hashing by pre-computing a hash map with prefixes as keys and their counts or indices as values. This method has a pre-processing complexity of O, n asterisk k, but allows for constant time lookups. The trade-off here is the extra memory required for the hash map, but it offers exceptional speed for queries.
Great job making it to the end.
To recap, we discussed the brute force approach to solve this problem, analyzed its time and space complexity, and highlighted key concepts. Remember, starting with a simple solution and refining it is often the best strategy.
Thank you for watching, and see you in the next problem-solving session.
That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!